Okay, so in this video we're going to cover power functions and polynomial functions. A power function is a function with a single term that is the product of a real number and a variable raised to a fixed number. A power function can be represented in the form f of x equals k times x to the p, where k and p are real numbers and k is called the coefficient. So here's some examples. Here's an example. Which of the following are power functions? So f of x equals x squared is a power function because it has a coefficient of 1 and it's times a variable x raised to a power of 2. So yes, this is a power function. What about 1 over x squared? Yes, that's also a power function because we can rewrite 1 over x squared as x to the negative 2. So we have a coefficient of 1 times x raised to a exponent of negative 2. Likewise, x to the negative 4th is a power function, so that's a yes as well. F of x equal to pi times x, well, we have a coefficient of pi times x to an exponent of 1. Okay, when we don't write the exponent there, it's understood to be 1. So f of x equal to pi x to the 1 is a power function. The function f of x equal to 2x times 4x to the 7th. Technically, as it's written, it's not a power function, but we could simplify that as a power function, though, to 2. It's a product of two power functions. And so we could get 2 times 4, which is 8, and then x times x to the 7th is x to the 8th power. So f of x is really a power function with a coefficient of 8 and times x to an exponent of 8. And so that's a power function. F of x equal to 3 to the power of x. That is not a power function. In fact, that's what we would call an exponential function. It's not a coefficient times x, and the x is being raised to a power. It's kind of like reversed. All right. The next function here, f of x equal to the rational function, which is x plus 3 over x squared minus 2. There's no way to simplify this to write this as a coefficient, a real number, times x to an exponent or a power, and so that's not a power function. Okay, so power functions are pretty straightforward. They're just a coefficient times a variable raised to some real number exponent. To discuss some what we call in behavior, or as x gets large, what happens to the outputs, we develop some notation. So to describe the behavior of numbers, we adopt the following notation. So we write x arrow infinity there. That means x approaches infinity, f of x approaches infinity. So when we see this, x approaches infinity, f of x approaches infinity, this means that x increases without bound or approaches positive infinity. And the outputs, f of x increase without bound or approaches positive infinity. Okay, so as x approaches infinity, f of x approaches infinity means what I underlined there. Similarly, we could say x approaches negative infinity, then f of x goes to positive infinity. So this means as x decreases without bound or approaches negative infinity, the outputs of f of x increase without bound or approaches positive infinity. Likewise, we could write as x approaches infinity, f of x approaches negative infinity. And this means as x increases without bound or approaches positive infinity, the outputs of f of x decrease without bound or approaches negative infinity. And the other combination you could have is as x approaches negative infinity, f of x approaches negative infinity. And this means that as x decreases without bound or approaches positive infinity, the outputs of f of x decreases without bound or approaches negative infinity. Okay, so that's notation we could use to describe what's called the in behavior. Okay, suppose you have a power function, f of x equal to k times x to n, where n is a non-negative integer. So think of some examples of that is like, say, x squared, x cubed, x to the fourth, x to the fifth, x to the sixth, etc., etc., etc. Okay, and so we have this little chart here which describes the in behavior of power functions. So remember, we could have a constant in front of all these powers here, right? These variables. And if k is positive and k is an even exponent, or excuse me, n is an even exponent, in other words, n is even, then we can describe the in behavior of a power function of the form kx to the n like this. Basically, it's going to look like a u for an even power. So that would be something like, I don't know, let's say, so k is positive, so like 2x squared, 2x to the fourth, 10x to the fourth, 5x to the sixth, where each one of these have a even exponent and a positive coefficient. It looks like this here. Okay, so what we're interested in is what happens as x gets really big, okay, in either the positive direction or really small, right, or gets big, I like to say gets big in the negative direction. What's going on with the y values? And what you'll see here is that the y values are getting increases as x goes to positive infinity, and it also increases as x goes to negative infinity. So we could write that or describe that as x approaches negative infinity, f of x goes to negative infinity. So that means basically shoots up, right? The y values shoot up as x goes to negative infinity. And as x goes to positive infinity, f of x, the y values shoot up that way. Okay, so that's an even positive power. All right, so then if n is an odd power, okay, so odd power, we might have, and k, the coefficient is positive. For instance, we could have something like 2x cubed, I don't know, maybe 1/5 x to the fifth power, 6x to the seventh power, etc., etc., like 7x to the 9. Then it's going to look like this. We're going to get a behavior that looks very similar to this graph here. Okay, and while we can describe what's going on, so as x goes to negative infinity, right, as we approach negative infinity in the x direction, what is the y values doing? Well, we can see that the graph is shooting down. So we could describe that behavior as x approaches negative infinity, f of x approaches negative infinity. That's what's going on here. We see that the behavior is shooting down. Likewise, if we go in the positive infinity direction, what are the y values doing? They're shooting up. And so we can just say x goes to positive infinity. As x goes to positive infinity, f of x approaches positive infinity. All right, once again, next row here. If k is constant, and if we have a negative, sorry, if our constant k is negative, and we have an even exponent, so basically if we had the same, examples here, except now if these were now negative coefficients, then what you're going to see is a shape that looks like this here. Okay, shape that looks like that. And well, if x is going to negative infinity, what is y values doing? It shoots down, right? The y values, the graph is shooting down, which means the y values are going to negative infinity. So we could say as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, right? As x goes to positive infinity, what are the y values doing? Well, they're shooting down to negative infinity. So we could say as x approaches positive infinity, the outputs, or f of x, approaches negative infinity. All right. Now the next part of this here is if we have, once again, negative coefficients, but this time our same kind of, we could have similar functions like negative 2x cubed, negative 1/5 x to the fifth, negative 6x to the seventh, negative 7x to the ninth. And if it has an odd exponent, once again, like we have here, and negative coefficients, then we see this shape here. Okay, and so to describe the in behavior, So in other words, as x goes to negative infinity, right? Negative infinity, what are the y values doing? Well, they're shooting up, meaning they're going to positive infinity. And as x goes to positive infinity, what are the y values doing? They're shooting down to negative infinity. You can see that by the graph. Okay, so that's called the in behavior. All right, I want to show you a little bit more about this using Desmos. So I'm going to write a function, a simple power function, f of x, and it's going to be equal to k times x to an even exponent. And the way you can write an even exponent is 2 times some integer. Okay, I'm going to create a slider for my n, and also create a slider for my k here. And right now, I'm going to leave my k as a positive number, but you can see that right now, if n is equal to 1, that means this is just x squared. But if I change n to say 2, and let me make sure it stays positive here. So we'll start at 2 and then go to maybe say 10 in steps of 1. Okay, so right now n is 2, so then, oops, let me double change it. Start at 1 here. Okay, so 1, so that means 2 times 1 is 2, so you get the shape. Let's change n equal to say 2. Well, once again, you still get that shape. This time, though, the exponent would be 2 times 2, which would be 4. So now that exponent's 4, and you get that shape. And so if we get n equal to 3, you notice it's kind of still the same shape, but it's getting more flat towards that 0 there, right? It's getting flatter. But now the exponent would be 2 times 3, which is 6. So if I go to 4, x equals 4, or n equals 4, so we get 2 times 4 is 8. So notice same shape, and if you observe, it's getting flatter by net 0. I'm just going to let this play here, and you can see that as n varies from 1 through n, the shape is basically the same, and you can see that the end values are changing. All right, let me stop that there. So right now n is 7, so that means this is x to the 14th. What is k doing though? So all it's doing is just multiplying that value, so it's getting narrower as they go up. But what happens if it becomes negative? We should see this flop downward. And you can see that. And likewise, if I change the exponent, once again, even exponents here, you can see the shape is still kind of that shape, but going downward and flat towards 0 there. Likewise, if I wanted an odd exponent, let me change this back to a positive 1 here, or positive 1 is fine. Let's change that back to a 1 there. So if I wanted this to be an odd exponent, then I could just say rewrite this as, oops, let's try this again, 2n plus 1. Not too sure why it's not working. Okay, so how about I write it like this? Not sure why that didn't work. Huh, interesting. Okay, so I have f of x equal to k times x to the n plus 1. Okay, so now I have a power function where the exponent is always odd, and so an odd exponent would have the form 2n plus 1 if n is an integer. And here I'm letting n going from 1 to 10. Okay, so you see it has this shape here as we saw in our table. Once again, if n right now is 1, so we get 2 times 1 plus 1, so that gives us 3. So if I give n equal to 2, that's 2n. So 2 times 2 plus 1 is 5, and so that's x to the 5th there, and then x to the 7th, x to the 9th, and so forth. But you can see, once again, and I'm going to let that play, all it is, it still has that kind of, I don't know, S type of shape, a sideways S type of shape, but you notice as n increases, or the odd exponent increases, it gets a little bit flatter around that 0 there. And how's that change if of k? Well, it's positive there, so right now n is 4, so we have 2 times 4 plus 1, so that's 8 plus 1 is 9, so we have this is x to the 9. And so k, if it becomes negative, you'll just see it flips over, right? You can see it flipping from, if it's positive, then to negative, you see it's negative k now, and it just reflects still sideways S, but reflected about the y-axis there. Okay, go ahead and let this play. You can see how it looks. Okay. And so that's the basically what the end behavior. That's basically the shape it takes on in the end behavior. It can be described by the ends of these graphs, okay, as we have done in the table. All right, let's go back to the notes. Okay, so we're actually to describe the end behavior of the power function f of x equal to negative 3 pi. Describe the end behavior of the power function. Okay, negative 3 pi x to the 6. All right, so we have a coefficient, right? Our k is equal to negative 3. That's our coefficient. It's negative. And our coefficient is negative 3 pi, not negative 3, but it's still negative. Our exponent, our power, or p if you want, is 6, so it's even. And so if you looked at if you go back to the table, we fall into what category? We have an even exponent and a negative coefficient. And so we are in this situation here. Okay, and so we could, if you want, draw a little simple graph here. So here's our x and y axis. Okay, and the reason why it's going to touch that origin at 0, 0 is because if you plug in 0, the output, an input of 0 gives an output of 0 there. And so the graph of this looks exactly the same as an even, so it's going to be looking like that. Pretty much flat, probably flatter than how I did it as we observed in the previous examples. Okay. And so how do I describe that end behavior? Well, I would say as x approaches negative infinity, my output function, or the output f of x, approaches negative infinity. Likewise, as x approaches negative infinity, or excuse me, positive infinity, my f of x approaches negative infinity. Okay. The next example here, describe the end behavior of the power function f of x equal to the square root of 4x to the 9th. So my coefficient k is going to be the square root of 3 over 9, which is positive. And we have an exponent, p, equal to 9, and it's odd. And so if you go back to the table, you'll see we'll fall in the case where k is positive and odd coefficient. And so let me draw a quick axis here. Here's my x-axis, and here is my y-axis. Okay, and the graph will look something like this. Let me do it a little bit better. Okay, it passes right through the origin there, and the end behavior would look like that. All right, so how do we describe that? Well, we can say that as x approaches positive infinity, or negative infinity, we'll go with negative infinity first, my f of x, my y values, so as x goes to negative infinity, right, it's going this way, what are the y values doing? They're shooting down, and therefore they're going to negative infinity. However, as x approaches positive infinity, f of x approaches positive infinity. And you can see that in the graph here, right? As x goes to positive infinity, the y values are shooting up, and therefore y goes to positive infinity. Okay, so let n be a non-negative integer, and let a sub n minus 1, a sub n 2, a sub 1, a sub 0 be real numbers with a sub n not equal to 0. So is a function that can be written in the form. So I'm missing a keyword here. And I have no idea why I'm missing that, but in other words, let's stop this sentence here. So this is one complete sentence. Let n be a non-negative integer, and let a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers with a sub n not equal to 0. Then we say a polynomial function. Somehow that's missing out of the notes there. So we'll put that right at the beginning there, or at the end of the there. And so a polynomial function is a function that can be written in the form f of x equals a sub n x to the n, and I got another typo here, plus, it should be a plus there, a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 a sub 2 x squared plus a sub 1x plus a sub 0. So that's a polynomial function. The degree of a polynomial is the highest exponent, so the n here would be the degree of the polynomial, and the a sub n x to the n is what we call the leading term, and the a sub n, the coefficient in front of in the leading term, is called the leading coefficient. And so we would say this is a polynomial of degree n. Of course, in practice, n is an actual number, say like 4 or 5. Okay, so let's look at the following. Which of the following are polynomial functions? So this first bullet point here, we have f of x equal to 2x cubed times 3x plus 4. Technically, how it's written, it's not a polynomial, but it's a product of polynomials. And so if you do the distributive property there, we get another polynomial. 2 times 3 is 6. X cubed times x will give us x to the 4th. And then 2x cubed times 4 gives us 8x cubed. And so you can see that's a polynomial of degree 4. G of x equals 4 plus 3x squared times 5x to the 8th. Once again, we could simplify this and write this as 4 plus 15, right? Because we have 3x squared times 5x to the 8. So 3 times 5 gives us 15. X squared times x to the 8 gives us x to the 10. So this would be a polynomial of degree 10. And then, so these are polynomials. Both of these are. But the last function here, h of x equal to 5 times the square root of x plus 2, is not a polynomial. Okay, here we have another exercise. We're asked to identify the degree, leading term, and leading coefficient of the following polynomial functions. All right, so let me just create a table here. So we'll have f of x, g of x, and h of p, and we'll specify the degree for each of these, the leading term, and the leading coefficient. All right. So the degree for f of x is the highest exponent. So you can see that we have degree f of x is a degree 3 polynomial. The leading term is the negative 4x to the power of 3. And the leading coefficient is a negative 4. G of x has a highest exponent of 5, so that makes it a degree 5 polynomial with a leading term of 5t to the 5th and a leading coefficient of 5. H of p has a highest degree of 3, so it's a degree 3 polynomial, and its leading term, for some reason, I have two, I just realized g of x has x as the input in the notation here, so let's cross that out. That should be t, since it's polynomial in variable t. All right, back to h of p. So h of p equals 6p minus p cubed minus 2. So the highest degree is, the highest exponent is 3, so it's a degree 3 polynomial. The leading term is minus p cubed, and the leading coefficient is negative 1. All right, so let me correct that g. That should read g of t instead of g of x. Okay. And so that's how you identify the degree, leading term, and leading coefficient of polynomials. Well, polynomials also have what's called an in-behavior, and you see how that works. Let's read this statement. So if a sub n, x to the n, is the leading term of a polynomial function, then the in-behavior of the graph as x approaches infinity or x approaches negative infinity behaves like the power function a sub n x to the n. In other words, what we're saying, as x approaches positive infinity or as x approaches negative infinity, basically f of x, whatever the polynomial is, whatever the polynomial function is, starts looking like its leading term. In other words, starts looking like roughly a sub n x to the n. Okay, in other words, as x gets really large in the positive direction or really small in the negative direction, it starts looking like the leading term. In other words, the leading term starts to dominate. Okay, so let's do a quick little table again. So if n is even and the leading coefficient is positive, then what we would see is very similar behavior as the leading term. Right, so the leading term, it looks like this, right? And so it would look similar to this in the end on its behavior. And what it's doing in between, we're not sure, but it at least the end parts will look like that. And if n is even, but a sub n is less than 0, then it looks like this. And then in between, we're not sure, but it's maybe zigzagging like that as well. If n is odd, but a sub n is positive, then it would look something like this. But we don't know what it's doing in the middle, but the end behaviors would look something like that. And if n is odd and a sub n is less than 0, then it would look something like this here. And we don't know exactly what it's doing in the middle, but the end behavior would look like that. And to explore this a little bit more, let's go back to Desmos. Let's go ahead and open up a new graph calculator there. And so let's just make up a quick polynomial. So for instance, suppose I have a polynomial p of x equals, say, 3x cubed minus 2x plus 3, something like that. Okay, so you can see that the end behavior kind of behaves like its leading term. What's its leading term? The leading term of the polynomial p of x is the polynomial 3x cubed. And you can see that in between, they don't look like each other, but if you say zoom out a little and take a look at, I'm going too far out, but if I kind of follow the graphs here, the red graph is the polynomial p of x, the blue graph is just the leading term 3x to the third, a simple power function. But as you trace the graph down, for instance, you'll see that eventually, I'm having trouble tracing, as x approaches negative infinity, you'll see that these values, the blue graph and it's kind of hard to see. Let me zoom out just a tad here. Zoom back, but let's zoom out a little bit. So let me go from, say, negative 100. You could, so negative 1000 there, or negative 100 here. You can see that they're getting very close to each other. They start looking like the same. In fact, you can trace it down and down. You'll see these graphs get closer and closer and closer. In fact, if I zoom out enough, you can't distinguish the two. So they start behaving much like each other once they get, as x shoots off to positive infinity and negative infinity. Likewise, suppose I had another function. Let me just zoom back home here. Say minus 2x to the fourth. Oops, what's going on here? X to the fourth minus 3x cubed minus x plus, I don't know, 1 or something. Okay, so then this polynomial would behave like negative 2x to the fourth, because that's the leading term. Oops, I put 3 there, 4. And you can see they're both shooting down. But if I zoom out far enough, you'll start seeing that the end behaviors, these graphs start appearing pretty close. In fact, let me just zoom out, say from negative, I don't know, 500 on the y. Okay, and you can start seeing that they're getting closer. In fact, I probably have to go a little bit further out. So let's go out to, say, negative 1000, maybe even further. Okay. Let me start at 0 there. And go steps in 10 or maybe 100. See if that helps. Okay. But you can see that as you zoom out, and I'm zooming out, they get closer and closer to each other. And it's kind of hard to zoom in and drag at the same time, but I encourage you to explore that. You can see they're getting closer and closer to each other as x goes to positive infinity or negative infinity. You can see that the two graphs start appearing the same. Okay, so that's the end behavior for polynomial functions. Let's return to the notes. Okay, so the next example here, we're asked to describe the end behavior and determine a possible degree of a polynomial function in the graph below. Okay, so from the graph, we can see the end behavior would be something like this. Well, as x approaches negative infinity, what are the y values doing? We can see that the y values are starting to shoot down, and that means the end behavior would mean f of x has to go to negative infinity. Likewise, as x approaches positive infinity, we can see that f of x approaches positive infinity. You can see that here, right, because the graph is shooting up. Okay, so that's the end behavior. Now, based on this picture, we don't know what exponent it would have, but the exponent would have to be odd exponent. And notice that since it's this an odd exponent, so remember it's going to behave like a polynomial function that has a leading term. Let me write that as a leading term as a sub n, x to the n. So this has to be odd. And based on the shape of the graph, we know that a sub n would also have the leading coefficient would have to be positive. Okay, but we can't figure out what degree it was. We could find out what degree it is, but we would have to study some other concepts like zeros and multiplicities. Okay, let's scroll down to the next example. So given the function f of x equals negative 3x minus 1, negative 3x squared times x minus 1 times x plus 4, express the function as a polynomial in general form, and determine the leading term, degree, and end behavior of the function. Okay, so we'll do some algebra here by expanding this function and writing it in standard form. Okay, or general form. All right, so let's multiply the parentheses, so we could FOIL there. And so foiling and combining our like terms, that would give us x squared plus 3x minus 4, and then we could distribute the negative 3x squared to get negative 3x to the 4th minus 9x to the 3rd, and then plus 12x. Okay, so notice the leading term here is negative 3x to the 4th. We have a degree 4 polynomial. Okay, we know that the end behavior is going to behave like the power function negative 3x to the 4th, the leading term, by what we discussed previously, and therefore what would the shape look like in the end behavior? Well, it's going to basically look like, say, downward, right? It's going to shoot downward. Who knows what it's doing in between? And then the right side will also shoot downward. That's how it would look if you follow the table above. Okay, so we could say that as x, the end behavior, right? As x approaches negative infinity, the graph of this has to shoot down. And so f of x would have to, the y values would have to go to negative infinity. Likewise, as x approaches positive infinity, the y values or the outputs have to go down to negative infinity as well. And I would encourage you to graph the function f of x and verify that it behaves like the leading term. All right, so finding the intercepts of a polynomial function. So one of the characteristics is, or that will help us sketch polynomial graphs of polynomial functions, is by finding or identifying where their intercepts are. So one, to determine the y-intercept, we could do that by finding the value of f of 0. So then the y-intercept is the value 0, comma f of 0. And then two, to determine the x-intercepts, we could determine the x-intercepts by finding the zeros, which is equivalent to solving the equation f of x equals 0. So if c is a solution, then the x-intercepts is c0. And I should be a little bit careful here. I should say if c is a real number solution, then the x-intercepts are where it crosses the x-axis is 0, c, 0. And I'm saying real number here because it's possible to get complex numbers, and that doesn't signify, it doesn't correspond to an x-intercept. All right, let's look at this next example here. Given the function f of x equals x to the fourth minus 4x squared minus 45, we're asked to determine the y and x-intercepts. All right, so the y-intercept is pretty straightforward. All you're doing is plugging in an input of 0. So we're just figuring out what f of 0 is. And so plugging that in, we get 0 to the fourth minus 4 times 0 squared minus 45. And so we get a value of negative 45 out. So the y-intercept would happen at 0, negative 45. All right, what about the x-intercepts? Okay, so that there means we solve the equation f of x equal to 0. So we have x to the fourth minus 4x squared minus 45. We got to solve this equals 0. Well, this factors has quadratic form, and it would factor as x squared minus 9 times x squared plus 5 equals 0. So using the zero factor property, we would first factor completely here. So x squared minus 9 factors as x minus 3 times x plus 3. Technically, we could factor x squared plus 5 using radical numbers, but I'm going to leave it alone like that and use the zero factor property. So we have x minus 3 is equal to 0, or x plus 3 is 0, or x squared plus 5 is 0. All right, so this would say x is 3 is the solution, x equal to negative 3 is the solution, but x squared equals negative 5, or x is equal to plus or minus the square root of negative 5, which gives us x equal to plus or minus I. Okay, so or not I, but negative 5 square root of, plus or minus the square root of 5 times I. It's an imaginary number. And so what are my x-intercepts? Well, the imaginary number don't correspond to x-intercepts, but my x equal to 3 and x equal to negative 3 do. So I would have 3, 0, and negative 3, 0 as my intercepts. So roughly, f of x would behave like its leading term if you're trying to discuss the end behavior. And so you might have a graph that looks something like this. And this is a quick rough sketch of it, not too accurate. We would have x-intercepts at negative 3, 0, and positive 3, 0. And it would have a y-intercept at 0, 0, negative 5. Sorry, negative 45. Not drawing a scale, by the way. 0, negative 45, way down here. And the graph, we know, would behave very much like a U-shape and shoot up like that. Okay, so that's it for this video.